Book 10, chapters 11 to 13 of 10 books on architecture. This LibriVox recording is in the public domain. Recording by Fredrik Karlsson. 10 books on architecture by Vitruvius, translated by Morris Hickey Morgan. Chapter 11. Ballistae. 1. Ballistae are constructed on varying principles to produce an identical result. Some are worked by hand spikes and windlasses, some by blocks and pulleys, others by capstans, others again by means of drums. No ballista, however, is made without regard to the given amount of weight of the stone which the engine is intended to throw. Hence their principle is not easy for everybody, but only for those who have knowledge of the geometrical principles employed in calculation and in multiplication. 2. For the holes made in the capitals, through the openings of which are stretched the strings made of twisted hair, generally women's, or of sinew, are proportionate to the amount of weight in the stone which the ballista is intended to throw, and to the principle of mass. As in catapults, the principle is that of the length of the arrow. Therefore, in order that those who do not understand geometry may be prepared beforehand, so as not to be delayed by having to think the matter out at a moment of peril in war, I will set forth what I myself know by experience can be depended upon, and what I have in part gathered from the rules of my teachers, and wherever Greek weights bear a relation to the measures, I shall reduce and explain them so that they will express the same corresponding relation in our weights. 3. A ballista intended to throw a 2-pound stone will have a hole of 5 digits in its capital, 4 pounds 6 digits, and 6 pounds 7 digits, 10 pounds 8 digits, 20 pounds 10 digits, 40 pounds 12.5 digits, 60 pounds 13.5 digits, 80 pounds 15.75 digits, 100 pounds 1 foot and 1.5 digits. 120 pounds 1 foot and 2 digits, 140 pounds 1 foot and 3 digits, 160 pounds 1 foot and a quarter, 180 pounds 1 foot and 5 digits, 200 pounds 1 foot and 6 digits, 240 pounds 1 foot and 7 digits, 280 pounds 1 foot and a half, 320 pounds 1 foot and 9 digits, 360 pounds 1 foot and 10 digits. 4. Having determined the size of the hole, design the scutula, termed in Greek peritretos, holes in length and 2 1/6 in breadth. Bisect it by a line drawn diagonally from the angles, and after this bisecting, bring together the outlines of the figure so that it may present a rhomboidal design, reducing it by 1/6 of its length and 1/4 of its breadth at the obtuse angles. In the part composed by the curvatures into which the points of the angles run out, let the holes be situated, and let the breadth be reduced by 1/6. Moreover, let the hole be longer than it is broad by the thickness of the bolt. After designing the scutula, let its outline be worked down to give it a gentle curvature. 5. It should be given the thickness of 7/12 of a hole. The boxes are 2 holes in height, 1 3/4 in breadth, 2/3 of a hole in thickness except the part that is inserted in the hole, and at the top 1/3 of a hole in breadth. The side posts are 5 holes and 2/3 in length, their curvature half a hole, and their thickness 37/48 of a hole. In the middle their breadth is increased as much as it was near the hole in the design, by the breadth and thickness of hole, the height by 1/4 of a hole. 6. The inner strip on the table has a length of 8 holes, a breadth and thickness of half a hole. Its tenons are 1 hole and 1/6 long, and 1/4 of a hole in thickness. The curvature of this strip is 3/4 of a hole. The outer strip has the same breadth and thickness as the inner, but the length is given by the obtuse angle of the design and the breadth of the side posts at its curvature. The upper strips are to be equal to the lower, the crosspieces of the table 1/2 of a hole. 7. The shafts of the ladder are 13 holes in length, 1 hole in thickness, the space between them is 1 hole and a quarter in breadth, and 1 1/8 in depth. Let the entire length of the ladder on its upper surface, which is the one adjoining the arms and fastened to the table, be divided into 5 parts. Of these let 2 parts be given to the member which the Greeks call cheloinion, its breadth being 1 1/6, its thickness 1/4, and its length 11 holes and 1/2. The claw projects half a hole and the winging 3/16 of a hole. What is at the axis which is termed the face? The cross pieces of 3 holes? 8. The breadth of the inner slips is 1/4 of a hole, their thickness 1/6. The cover joint or lid of the chelonium is dovetailed into the shafts of the ladder, and is 3/16 of a hole in breadth and 1/12 in thickness. The thickness of the square piece on the ladder is 3/16 of a hole. The diameter of the round axle will be equal to that of the claw, but at the pivots 7/16 of a hole. The stays are holes in length, 1/4 of a hole in breadth at the bottom, and 1/6 in thickness at the top. The base, termed escara, has the length of holes, and the anti-base of 4 holes. Each is 1 hole in thickness and breadth. A supporter is jointed on halfway up, 1 1/2 holes in breadth and thickness. Its height bears no relation to the hole, but will be such as to be serviceable. The length of an arm is 6 holes, its thickness at the base 2/3 of a hole, and at the end 1/2 a hole. I have now given those symmetrical proportions of ballistae and catapults which I thought most useful, but I shall not omit, so far as I can express it in writing, the method of stretching and turning the strings of twisted sinew or hair. Chapter XII. The stringing and tuning of catapults. 1. Beams of very generous length are selected, and upon them are nailed socket pieces in which windlasses are inserted. Midway along their length the beams are incised and cut away to form framings, and in these cuttings the capitals of the catapults are inserted, and prevented by wedges from moving when the stretching is going on. Then the bronze boxes are inserted into the capitals, and the little iron bolts, which the Greeks call epizygides, are put in their places in the boxes. 2. Next the loops of the strings are put through the holes in the capitals and passed through to the other side. Next they are put upon the windlasses and wound round them in order that the strings, stretched out taut on them by means of the handspikes, on being struck by the hand, may respond with the same sound on both sides. Then they are wedged tightly into the holes so that they cannot slacken. So, in the same manner, they are passed through to the other side and stretched taut on the windlasses by means of the handspikes until they give the same sound. Thus, with the tight wedging, catapults are tuned to the proper pitch by musical sense of hearing. On these things I have said what I could. There is left for me, in the matter of sieges, to explain how generals can win victories and cities be defended by means of machinery. Chapter XIII. Siege machines. 1. It is related that the battering ram for sieges was originally invented as follows. The Carthaginians pitched their camp for the siege of Cadiz. They captured an outwork and attempted to destroy it, but having no iron implements for its destruction, they took a beam, and, raising it with their hands, and driving the end of it repeatedly against the top of the wall, they threw down the top courses of stones, and thus, step by step, in regular order, they demolished the entire redoubt. 2. Afterwards, a carpenter from Tyre, bright by name and by nature, was led by this invention into setting up a mast from which he hung another crosswise like a steelyard, and so, by swinging it vigorously to and fro, he threw down the wall of Cadiz. Geras of Chalcedon was the first to make a wooden platform with wheels under it, under which he constructed a framework of uprights and cross pieces, and within it he hung the ram, and covered it with ox hide for the better protection of the men who were stationed in the machine to batter the wall. As the machine made but slow progress, he first gave it the name of the tortoise of the ram. 3. These were the first steps then taken towards that kind of machinery, but afterwards, when Philip, the son of Amyntas, was besieging Byzantium, it was developed in many varieties and made handier by Polyidus the Thessalian. His pupils were Diades and Carius, who served with Alexander. Diades shows in his writings that he invented movable towers, which he used also to take apart and carry round with the army, and likewise the borer and the scaling machine, by means of which one can cross over the wall on a level with the top of it, as well as the destroyer called the raven, or by others the crane. 4. He also employed the ram mounted on wheels, an account of which he left in his writings. As for the tower, he says that the smallest should be not less than 60 cubits in height and 17 in breadth, but diminishing to 1/5 less at the top, the uprights for the tower being 9 inches at the bottom and 1/2 foot at the top. Such a tower, he says, ought to be 10 stories high, with windows in it on all sides. 5. His larger tower, he adds, was 120 cubits high and 23½ cubits broad, diminishing like the other to 1/5 less. The uprights 1 foot at the bottom and 6 digits at the top. He made these large towers 20 stories high, each story having a gallery round it 3 cubits wide. He covered the towers with rawhide to protect them from any kind of missile. 6. The tortoise of the battering ram was constructed in the same way. It had, however, a base of 30 cubits square and a height, excluding the pediment, of 13 cubits. The height of the pediment from its bed to its top was 7 cubits. Issuing up and above the middle of the roof for not less than 2 cubits was a gable, and on this was reared a small tower 4 stories high, in which on the top floor scorpiones and catapults were set up, and on the lower floors a great quantity of water was stored to put out any fire that might be thrown on the tortoise. Inside of this was set the machinery of the ram, termed in Greek kriodike, in which was placed a roller turned on a lathe, and the ram, being set on top of this, produced its great effect when swung to and fro by means of ropes. It was protected, like the tower, with rawhide. 7. He explained the principles of the borer as follows: that the machine itself resembled the tortoise, but that in the middle it had a pipe lying between upright walls, like the pipe usually found in catapults and ballistae, 50 cubits in length and 1 cubit in height, in which a windlass was set transversely. On the right and left at the end of the pipe were 2 blocks, by means of which the iron-pointed beam which lay in the pipe was moved. There were numerous rollers enclosed in the pipe itself under the beam, which made its movements quicker and stronger. Numerous arches were erected along the pipe above the beam which was in it, to hold up the rawhide in which this machine was enveloped. 8. He thought it needless to write about the raven, because he saw that the machine was of no value. With regard to the scaling machine, termed in Greek epibathra, and the naval contrivances which, as he wrote, could be used in boarding ships, I have observed that he merely promised with some earnestness to explain their principles, but that he has not done so. I have set forth what was written by Diades on machines and their construction. I shall now set forth the methods which I have learned from my teachers and which I myself believe to be useful. End of Book 10, Chapter 13.